Good morning, student. In this lecture, we will study about the multiple bridge converters. Name of topic is multiple bridge converter. So what is a multiple bridge converter? Till now we have studied the only bridge type of converter, 6 pulse converters. They have only 6 valves. So multiple bridge converter is nothing but the series connection of number of bridges. So that called as a multiple bridge converters. When 2 or more bridges are connected in series, to obtain as high direct voltage as required. So it means when you require the high direct voltage at the DC side, at that time you connect the 2 or more number of bridges in series at the DC side. Clear? So that is called as a multiple bridge converters. So let's draw the single line diagram first for the 12 pulse converter. We have already seen this in the one of the practicals. I think second practical we have seen the 12 pulse converter, 18 pulse converter and 24 pulse converters. So that concept we have study again theoretically. So let's start the single line diagram for this. So this is a one transformer, RYB phase, primary star connected, secondary is also star connected. This is the smoothing inductor, LD, positive polarity. So this R phase that is connected with first leg, Y phase that is connected with the second leg, and B phase that is connected with the third leg. This is R, Y and B. So this is a one bridge. There are total 6 valves. Give the name 1, 2, 3, 4, 5 and 6. Same type of 6 pulse bridge converter, 6 pulse converter or 3 phase bridge converter that is connected in series with these converters. So here again there are converter transformer, primary star connected, R, Y and B phase. Secondary is now delta connected. This is R, Y and B. Same type of bridge converter, R phase first leg, this is a thyristor base, Y phase with the second leg and B phase with the third leg. This is the third leg, B phase. So this is connected in series here. Clear? And this is a negative terminal. So you get the voltage between first terminal of this converter, which is positive, and negative terminal is the second leg of this another 6 pulse converter. So load is connected here between positive of first converter and negative of the second converters, because both are connected in series. So whenever we require the high voltage at the DC side, at that time we connect this two bridges in series. So here two bridges connected in series, each are a 6 pulse converter. So you must get the 12 pulse at the output side, or you get the 12 pulse in one cycle of the output voltage. But when you get the 12 pulse, if there is a 30-degree phase shift between the supply of first bridge and second bridge. So here that's why we take the star-star transformer in the first converter, and second converter supply we given through the star delta transformers. So between this two three-phase supply, there is a 30-degree shift, because here secondary is star connected, here secondary is delta connected. So that's why between these two three phases the angle difference is 30 degree. It means suppose this R phase is given at the 0 degree, then this R phase is given at the 30 degree. Clear? So there is a 30 degree phase shift between each phases. So that's why you get the 6 plus 6 12 pulse at the load side. So what is the advantage of this multiple bridge converters or multiples bridge converter? The advantage is that as you get the number of more pulses in one cycle at the output side, the harmonic reduces as well as ripple is reduces. So you require the small size of the filter at the load side as well as DC side as well as AC side. Load here suppose is a DC, so DC side also harmonica reduces. Same way the harmonics also reduces at the AC side. Because of the switching of this converter, some of the harmonics are injected to the AC side. So you have required the filter at the AC side also. But if you use the multiples converter, the lower order harmonics magnitude reduces, because we already taught that in the 6 pulse converter, the order of harmonics that is injected to the AC side harmonics in the 6 pulse converter, that order is NP plus minus 1. N is integer number 1 to up to infinite, and P is a pulse. It is a 6 pulse converter, so P is equal to 6. So here for N is equal to 1, P is equal to 6. The order of harmonic you get at the AC side is how much? First is 5th and second is 7th. P is 6, N is 1, so 6 plus minus 1, so 5th and 7th lower order harmonics you get, which is a dominant harmonic. Same way put N is equal to 2, P is remain same because it is a 6 pulse converter. So that becomes 12 plus minus 1, so it is 11 and 13. Clear? So same way as the higher order harmonic you get, but starting from the 5th and 7th. So here the lower order harmonics is a 5th and 7th, which frequency is smaller as compared to this higher order harmonics. So as we know that as the frequency of the harmonic are less, you require the large size of the filter, because the filter component L and C, that is inversely proportional to the frequency. So if the frequency of the harmonic is less, you require the large size of L and C. It means large size of filter you require to filter out the lower order harmonics. Clear? But if you use the 12 pulse converter, at that time the order of harmonic is 2 NP plus minus 1 in 12 pulse converter. So here again N is equal to 1, 2, 3 up to infinite. P is equal to here 12, because we take the 12 pulse converter. We combine this 6 pulse and 6 pulse. So that becomes 12 pulse. So here in the 12 pulse, P is equal to 10. For N is equal to 1. So what becomes here? Sorry, here it is NP plus minus 1, not 2NP. So here P is equal to 10, N is equal to 1. So lowest order of harmonic is 11 and 13. It means here you eliminate the 5th and 7th harmonics that you get in the 6 pulse converter. So it means that in 12 pulse converter you not get the 5th and 7th harmonics. So you can see that here the lower order harmonic or dominant harmonic frequency, which is more than the dominant harmonic frequency which you get in the 6 pulse converter. Clear? Obviously 11th and 13th order harmonic frequency is more than 5th and 7th. So here same way again the filter size It means L and C component required here in the 12 pulse converter in this case is smaller as compared to the 6 pulse converter, because here order of the harmonic is 11 and 13. So 11th order harmonic is how much? Frequency is how much? 11 multiply 50. 50 is the fundamental frequency. So 11 multiply 50, so it is a 550. Clear? And 30 multiply 50, so it is 650. So you design this L and C for the 550 and 650 hertz frequency. Clear? And here in the 6 pulse converter, dominant harmonic is 5th and 7th. So 5th order means 250 hertz and 7th means 350 hertz. So you can see that this harmonics frequency in the 12 pulse converter, which is more than the harmonic frequency, dominant harmonic frequency in the 6 pulse converter. So that's why in the multiple bridge converters we require the small size of the filter, because L and C is inversely proportional to the frequency. So I hope you understand that why we require the multipulse converters. So again you can add up the next 6 pulse converter in series with this, so that becomes just 18 pulse converters. So it means that you get the 18 pulse in one cycle. So again the dominant harmonic frequency is become more, as like equation NP plus minus 1, now P is becomes 18. So you get the dominant harmonic 17 and 19. So 17, 19 dominant harmonic frequency is more than 11 and 13 and 5th and 7th. So that's why the size of filter is again you can reduce. Clear? But the problem is that as you increase the number of pulses or number of bridges connected in series, you require the complex connection of the converter transformers. So generally we prefer to use the up to the 12 pulse converter, not go for the higher number of pulses like 18 pulse, 24 pulse, 36 pulse. We can use this type of multipulse converter, but problem is that the connection of the transformer becomes more complex. Clear? So that's why generally in the practical situations we prefer to use the 12 pulse converters. Clear? So that 12 pulse converter also the dominant harmonic frequency is more as compared to 6. So again you require this small size of the filter. So it is a cost effective. So this is the advantage of 12 pulse converter, or you can say the multipulse converters. So let's we graphically see this, or by using the waveform we will see that how this waveform we get in the 12 pulse converter. So as we see that in the 6 pulse converter we connect the two 6 pulse converter. You can see here one is star star and another is a star delta connected supply. So one by one we see the waveform for the star star, then star delta, and then after combining these two converter we will see that what is the output you get at the load side, or what one star delta connected transformer with 6 pulse bridge converter. So what is the output of this bridge type converter at the DC side as well as AC side? So let's see this. So suppose DC side here, DC voltage, in this case suppose you get this type of waveform at the DC side, and AC side you get suppose this type of waveform. Yeah. Same way second converter is a star delta, a star star connected, star star connected. In this case you get the waveform at the DC side, suppose like this. AC side, suppose you get this type of waveform. So this is a waveform at the AC side. This is a waveform at the DC side. This is a waveform for star delta connected DC side. This is a star star connected DC side. And this is a AC side, star delta connected and star star connected, this type of waveform. Now you combine both this, because we make the 12 pulse converter by combining these two. So in this case, here we have star delta, another is star star, six pulse converter, this one, this is another 6 pulse converter, and both are connected in series, and the output you get, that is a 12 pulse. So in this case you get the output 12 pulse. So in this case you get the 12 pulse output. Clear? Half cycle you get only 6 pulse. Clear? So what is a waveform at the AC side you get here? So AC side you get the waveform like this way in step form. If you combine in this both the waveforms, this one and this one, if you combine both this waveform, so you get the addition of both this waveform in the 12 pulse converter like this way. Sorry, this one. So you get this type of wave shape. So you can see that this waveform at the AC side, which is more near to the sinusoidal as compared to these two waveforms. It means this two waveform has high harmonic content as compared to this 12 pulse converter AC side output voltage. So that's why we require the multi-pulse converter, because in the 12 pulse converter the order of the harmonics are less, or the amount of total harmonic distortion is less as compared to the 6 pulse converters. So this is the advantage of using the 12 pulse converter, or you can say the multi-pulse converters. As you increase the number of pulses like 18 pulse, 24 pulse, again you get the output, or AC side voltage which is more near to the sinusoidals, and the magnitude of the ripple is again reduces. So here in the 12 pulse converter, this width of each pulse is 30 degree. So you get the 12 pulse. So in the one cycle, it means 360 degree, you get the 12 pulse. Each pulse is 30 degree width. Clear? So I hope you understand the concept of multiple bridge converters. Now next, we understand that the relationship between AC and DC quantities in the multiple bridge converters. In the last lecture we have studied the relationship between AC and DC quantities, but that is just for only the 6 pulse converters or 3-phase bridge converters. Now here we will study this relationship between AC and DC quantities with multiple bridges. So now let's draw the single line diagram. This is a converter. This is a converter transformer. Suppose this transformation ratio is 1:T. Suppose B number of bridges are connected. B number of bridges is the number of bridges are connected in series. B is nothing but number of bridges in series connection. T is the transformation ratio because it is 1:T. So T is the transformation ratio. Now as we know, the ideal nodal voltage we have derived the equation of VD0, ideal no load voltage. VD0 is equal to 3 root 2 divided by pi into ELL in terms of line to line voltage. But here we use a number of bridges B times number of bridges in connected in series. So what is the average direct voltage at no load condition? So that is B times as well as transformation ratio times 3 root 2 by pi ELL. So this is the equation of ideal no load voltage for the multiple bridge converters. VD0 3 root 2 ELL by pi, that we have already derived, that is for 6 pulse converter. But here there are number of bridges are connected in series. How many numbers? So that is B numbers. B is maybe 2, 3, 4, 6 like this way. If it is a 12 pulse converter, then number of bridges connected in series is 2. So B is 2 and multiply with the transformation ratio T. So that gives the ideal no load voltage. Now as we know that the voltage drop in the converters, voltage drop in one bridge or 1/6 pulse converter, that is 3xc by pi into ID. That is a voltage drop. RC into ID. RC is nothing but 3xc divided by pi. Clear? So that is the voltage drop in one bridges. Here how many bridges? B number of bridges. So how much voltage drop? So that is a 3xc divided by pi into ID into B times. Clear? So now as we know the equation of VD, direct voltage, VD is equal to VD0 cos alpha minus RC ID. Clear? So VD0 cos alpha, this voltage drop is nothing but this one, 3xc divided by pi into ID into B. Clear? So this is a modification of average direct voltage here in the multiple bridge converter. Changes is what here in the voltage drop, multiply with the B. B is nothing but number of bridges connected in series. Clear? If you connect the two number of bridges, it means you make the 12 pulse converter. So your voltage drop is 2 times the voltage drop happens in one bridges. Clear? So same way another equation you can write from the inverter point of view. We have derived the equation VD is equal to VD0 cos gamma minus RC into ID. So same way you can write VD0 cos gamma minus same way 3xc by pi ID into B. Clear? In terms of power factor, we can also derive the last lecture we derived the equation VD is approximately is equal to VD0 cos phi. Clear? So here in this equation your VD0 value you put here this value 3 root 2 by pi ELL B into T. In the normal 6 pulse converter, VD0 is only 3 root 2 by pi ELL. But in the multiple bridge converter, VD0 value is 3 root 2 by pi ELL B into T. Clear? So put this value of VD0 in this equation. So that gives the average direct voltage. Clear? So you can use any of the equation to derive the direct voltage. In the inverter operation, you use this equation. Rectifier operation, you use this equation. And suppose if you know the value of cos phi power factor, then based on this equation also you can find out the average direct voltage. Same way, in one of the last lecture we have derived the equation of ID, current ID and current IL1, relationship between ID and IL1. IL1 is nothing but RMS value of fundamental frequency component, fundamental frequency component of the AC current. So IL1 is equal to root 6 by pi into ID. That equation we have derived in the one of the last lecture. Clear? So here in the multiple bridge converter, this is the equation for 6 pulse converter. But for the 12 pulse converter, the relationship between the RMS value of fundamental current and ID is IL1 is equal to root 6 by pi into beta into T into ID. So this is equation for IL1 for 12 pulse converters. So here this is a modification in the fundamental frequency component of the line current in the 12 pulse converters, or you can say that in the multi-pulse converter. So here suppose you use the 12 pulse converter, so it is a B is equal to 2, B is equal to 2 for 12 pulse converter, B is equal to 3 if you use the 18 pulse converter, B is equal to 4 if you use 24 pulse converter. So based on the multi-pulse converter you have used and transformation ratio, put the value here and find out the fundamental frequency of the line current. So there is a change only in the relationship between the AC and DC quantities of multiple bridge converters and normal 6-pulse bridge converters. So I hope you understand this concept. So in the next lecture we have studied the example related to the multiple bridge converter as well as the 6-pulse converters. Thank you.